Hello, in this e-learning video, I'll be talking about Simcyp's Power Calculation tool. For this, I'll start off with a brief background on what power analysis is. When we design a clinical trial, there are various aspects to consider. The first is the sampling design. This is the design of how to select the items to be observed for the study. The next component is the observational design, which is a condition under which the observations are to be in. And finally, we have the statistical design, which is how the information is gathered and should be analyzed. All of these components help us to answer our research question. For this e-learning video, we'll be focusing on the sampling design component, specifically on how to calculate the sample size required for a study. What is a sample size? A sample is a subpopulation that is studied to make an inference about a repopulation. In research, due to constraints such as time and budget, a representative sample is normally used. If the sample is too large, although this would mean that the results will be more accurate, this large sample can also be very expensive. On the other hand, if the sample is too small, then we may fail to detect the important effect or association. Therefore, it is important to determine the optimum sample size. This is a sample size necessary to claim the true treatment effect exists. So this is where power analysis comes into play. What is power? Power is a probability, and it is defined as the probability of correctly rejecting the null hypothesis. To calculate the power, the null hypothesis test states that population 2 is equal to population 1. In other words, they have the same mean and the same variance. Typically, at least 80% power is the target. In a clinical trial, it is important to minimize the chances of making the wrong decision. In other words, minimize the probability of committing type 1 and type 2 errors. What is type 1 and type 2 errors? Type 1 error, also called alpha, is a probability of rejecting a null hypothesis when it is true. And type 2 error, also known as beta, is a probability of accepting a null hypothesis when it is not true. So if we look at this orange table, we can see that within the table, on the left-hand side is the decision made by the test statistics. And on the right-hand side, we have the truth about the null hypothesis. So in this case, when the null hypothesis is true, and then we reject the null hypothesis, this is known as a type 1 error. And when the null hypothesis is true, and we fail to reject the null hypothesis, so this means we have correctly accepted the null hypothesis, this is known as our confidence level. On the other hand, when the null hypothesis is false and we reject this null hypothesis, this means that we have correctly rejected the null hypothesis. This is known as the power. However, when the null hypothesis is false and we fail to reject the null hypothesis, this is known as type 2 error, in other words, as beta. Therefore, our aim is to minimize both alpha and beta in a test, and as a result, the power of the study, which is the probability of correctly rejecting the null hypothesis, and our confidence level will increase. So the main question in power analysis is, what is the sample size such that at 1 minus alpha % confidence level, the null hypothesis will be correctly rejected 1 minus beta % of the time? So if we assume alpha is equal to 0.05 and 1 minus beta, which is the power, is 0.8, we can rephrase the question and say, what is the sample size such that at 95% confidence level, the null hypothesis will be rejected at least 80% of the time? In other words, we want to find a sample size that is capable of correctly depicting the difference between two population groups if the difference is true. And we also want to have confidence that if we resample, the results will be reproducible 95% of the time. In other words, at 95% confidence level. So if I open up Simcyp, the power calculation tool can be found in the outputs. So if you click on outputs and then you go into data analysis, now you can see the power calculation tool. At the moment, this feature is grayed out. This is because the power calculation tool is only available when you use multiple population within the workspace. So if I go back to trial design and then I click on multiple population, I can now activate the number of population I wish to use. Do make sure that the number of subjects in each population sums up to the total number of subjects in your trial section. After this, I can now select the population I wish to compare. So I'm going to compare healthy volunteer with renal populations, with all the renal populations. So the first population will be renal mild. And then I'm going to select moderate renal impairment and then severe renal impaired. Now I can go back to my outputs and then data analysis, power calculation. Now I have the option to activate this feature. In this tool, you have the option to use either substrate plasma or substrate blood. I'm going to use substrate plasma. Then you have the option of AUC calculations. For this, I'm going to use AUCT. Then you need to select the populations that you wish to compare. The maximum number of population is 2. So here I'm going to compare healthy volunteers with mild renally impaired population. For the first population, you need to specify the minimum number of samples and the maximum number of sample, as well as the step size. And then for population 2, you have the option to either make the sample of population 2 equal to population 1, or you can choose to make it a ratio. If the ratio is 2, then this means that if the sample for population 1 is, for example, 10, then the sample that will be generated for population will be 10 times 2, which is equal to 20. I'm going to keep it as the population of 2 is equal to population 1. Then you should specify your alpha level. An alpha of 0.05 means that we are going to be testing at 95% confidence level. And then you need to specify the PK parameter that you wish to compare. I'm going to keep it as AUC. Once you've set all your parameters for this power calculation tool, then you can run your simulation and you should get your outputs in Excel. So for this example, I've compared the healthy volunteer with the mild renally impaired population. Once the output is done, you should see an Excel sheet which looks like this. In this Excel, you can go into the study power sheet. Here you can see a power analysis between healthy volunteer and renally impaired population. At the bottom, you can see the results. The first column shows when the sample is equal to 3. So when the sample is 3 for population 1 and population 2, we have a power of 63.86%. However, when the sample goes up to 9 for population 1 and we have 9 samples for population 2, we can see that the power increases to 91.28%. This is beyond the 80% power requirement. Therefore, we can say having a sample size of 9 subjects in population 1 and in population 2 is enough to depict the true difference in AUC between the two populations. Having a higher number of sample size increases the power. So the more sample size you have, the more power you will get at depicting the difference between AUC between the two populations. I have already gone ahead to carry out the power analysis calculation for the other renally impaired population using AUC data. And here is the result. So what we can see here is this is the result for the mild population power analysis calculation compared to the healthy volunteer, and then for the moderate renally impaired population, and then for the severe renally impaired population. What we can see is that the power for the mild population is lower compared to the severe population. In fact, we can say a sample size of n equals 3 is enough to depict the difference between the true AUC between the two populations, in this case, healthy volunteer and the severe renally impaired population. So we can conclude that power is influenced by the difference between the two populations. The larger the difference, the more power you have. Also, power is influenced by the number of sample. So the more sample size you have, the more power you would also have. Thank you very much for listening.